Hey, you're 12! Woo! Good to see you. Thanks for coming, everybody. We're doing well on the register this morning. How's everyone coping? Is everyone all right? I know it's a tough situation, isn't it? Is anyone starting to feel a bit like me? Feeling a little bit cabin fever-esque? Feeling a little bit like, whoa, just want to get out and see people. We'll see normal people. I'm just going to hang on for a couple more minutes before I start the lesson just to see how many more people show up. We're missing a couple. We're doing all right. Haven't got Dat yet. Dat's missing. Still missing Ben, Mika, and Donna. Let's see how long it takes before those guys show up. I will start in a couple of minutes, though. Right, so today, I need a new book, says Ivan. Like it. Ivan, take your notes on your MacBook. Oh, hang on. You're watching a video through your MacBook. Maybe write on paper? I don't know. I've got some paper here if it'll help. I don't think it will, though. I could try and mail it to you through YouTube. Oh, there's Donna, there's Mika. Yeah, we're nearly there. Look at that. Still missing Ben. I think Ben and Dat. Only two. All right. So okay, guys. Today, we're actually nearing the end of Unit 2 at this point. I will, of course, then start the revision. I'll continue to remind you guys, you need to be having a look at those booklets that are on the sheet that I've made for you guys. Yeah, keep doing the questions. I'll post some more online on the classroom, some more booklets and some more questions. But those really are your ticket to your grades, really. Just make sure you're doing it. There's Dat. One to go, just Ben. Okay, let's crack on. Let's see if I share my screen. There we go. Then click on that guy and then do hide. And then I'm going to disable my camera so it stops running. Gives me a little bit more time before my screen goes shaky. Right, so today's lesson. We're looking at infrared spectroscopy. Right, let's see if I can lay this thing flat. Oh, sorry, didn't mean to do that, folks. There we go, click back on that. Open up my little kickstand here at the back. There we go. Nearly there. Nearly there. Right. Okay, so learning objectives today, folks. I've actually already put them onto the YouTube video. Figured I might start doing that. I think it's quite a nice way to do it. So you guys need to understand bond absorbance. Absorbance. You also need to be able to identify particular bonds. So different bonds have different absorbances. And the last one, which is to understand how IR explains global warming. Cool. Okay. And the last thing I'm going to do, I'm just going to tack on be able to do exam questions. I'll see if I can tie in some exam questions today in this webinar. Still missing. Oh, Donna's there. I've got Donna. Wait, we have Donna. Is that everyone? No, I've got Ben. Ben's still missing. Is Ben sleeping in? Can someone message Ben, please? That would be super handy. Thanks, guys. Okay. All right. So, okay. So we've been over the course of chemistry, and this isn't even an A-level focus. This is just throughout your chemistry education. You've been studying parts that enable you to identify, analyze particular compounds. Now, you could call this analysis. So the key here is analysis. Sometimes I like to call it structural. This is actually a name, structural determination. determination. Na, na, na. There we go. So the idea of this is we run analytical processes in order to determine who somebody is. Now, in reality, oh, Suvat. Yeah, oh, Ben's here. Wah! There's Ben. Hey, Ben. Good to see you, dude. You're in. Full house. Full house. Whoop, whoop. I think that's sent. Yay, it's all there. Win it. So, do you know what? It is nice for us to kind of talk a little bit about analysis. And just, this is kind of like a big umbrella term. And we've covered various things in analysis. So the first thing we did, part of GCSE, is chemical analysis. I'm going to put chemical tests because it's actually easier to understand. So you guys have been learning chemical tests for years. This is silver nitrate for halide ions. This is sodium hydroxide for metal ions. This is flame tests for metal ions. This is add acid for carbonates, add hydrochloric acid followed by barium chloride for sulfate ions. Chemical tests, these are, and these are not gone. The GCSE ones, GCSE, still stand. And now we pick up new ones at A level. I'm actually gonna do a revision lesson on this next time. Next lesson. I'm just gonna do the whole of chemical tests in one go. I feel like that would be a really beneficial webinar for me to be able to do and keep. And we've been slowly adding on to this at A level. So we've just recently picked up the tests for aldehydes and ketones, being Tollens reagent or Fehling's reagent. We've picked up the test for alcohols, add sodium metal, or add potassium dichromate and dilute sulfuric acid. We are collecting chemical tests. Then what we have is, we then have rather than chemical testing, we also have machine testing. Now, I'm actually going to split this into two. So I'm going to do machine analysis. So machine analysis is then split into things like mass spec. Now, I was actually going to do a lesson on mass spec today, but I realized I've done most of the AS bit with you guys already, which is good. I will do a revision lesson on it anyway. But this, of course, is looking at parent peaks, parent stroke molecular ion peak. But we've already done it. Molecular ion peak. I'll put peaks or peak. And then it also looked at fragmentation. Fragmentation patterns. I'm trying to think of any others. There is an extension to this for A2, by the way, which is called major and minor fragmentations. But I'm not going to do that because it's part of the A2 specification. But it's something, if you want to just make a note of that, which is see later notes. This is major / minor fragmentations. This is see later notes, frags. I'm just going to put frags. Yeah, this is A2. See later notes. See later notes. The next one is we then have infrared, IR. We then have NMR. This is A2. NMR. You can put A2 on that one underneath. See later notes. This is AS. This is AS and A2 mass spec. AS/A2. Yeah, it's good to do that. There is one more as well, which is chromatography. And chromatography. So it's the chromatography song, big hit in the 60s. So chromatography, again, is A2, really. I know it's funny that because you did chromatography in year 7 and then it reappears back in A2. So, okay, so today we're focusing on IR, and all of this is part of structural determination. All of this will allow us, when we run all of these processes, it's going to allow us to be able to determine what something would be. Okay, so first thing is we need to state what infrared spectroscopy is. Oh, I've suddenly realized there's another one. There's another one as well. You can, oh, I want to make that nice and straight because it looks cool. Oh, sorry, folks. There we go. You've also got colorimetry as well. I always forget that one. Colorimetry. This is A2 again. And this is looking at colors. This is otherwise known as, this is infrared spectroscopy. That's with infrared light. Colorimetry is actually visible light spectroscopy. Visible light spectroscopy. Spectroscopy. There we go. Visible light spectroscopy. And that one again is part of A2. And it's actually covered in biology as well, but we do a little bit more in terms of chemistry. Okay, so what exactly is IR? So infrared. Infrared. I've lost my mind already. Infrared spectroscopy. Okay, so spectroscopy. So would everyone agree chemical tests will help us identify ions? So I'm going to change my color. This chemical tests will help us identify ions. It helps us identify families in organics, homologous series. Yeah, it's going to help us identify families such as aldehydes and ketones, alcohols, etc. Double bonds, alkenes. Yeah. What else does chemical tests allow us to do? Not an awful lot. It kind of covers all bases, really. Ions and families. Spectroscopy, the machine analysis is more than that, because I think what you'd all agree. Oh, yeah. I think what you'd all agree is there's a problem with this. There's limitations to chemical analysis. The limitation is things like isomers. That's a problem for chemical analysis. Just to show you an example of this, I'm trying to zoom in and give myself some space. I'll move up a bit. There we go. Found a bit of space. So limitation to chemical, limits to chemical tests. Well, if we look at something like, let's just choose somebody. Let's choose a secondary alcohol. Guys, so first question of the day, can you pause the video and can I have a go? I've given you the start of the molecule. Can you now turn that into a 4-carbon secondary alcohol, please? Pause the video and have a go at it. And I've deliberately done this in this regard, folks. Yeah, I've given you a starting structure, 4 carbons, secondary alcohol, please. So pause the video. Brilliant. So the reason why that's a little bit tricky is because there's a bend in it. Lots of people think that this is going to therefore become perhaps a tertiary, but in terms of, it makes no difference that there's a bend in this. Yeah, bends are normal. Bends are normal. Oh, there's Winkit. Winkit's arrived. Oh, hi, Winkit. Nice to see you. Glad you could come along. So there's a Ben in it. Ben, like Suva? No, oh, sorry. So this is butan-2-ol. Yeah, secondary alcohol. Okay, so would we agree that we can, in a chemical test, we can certainly A, use acidified potassium dichromate, dill sulfuric, and K2Cr2O7. We can definitely do this to prove it's an ol group. Oh, I've got a better idea, look. To prove that this is an ol group. There we go. Do you see what I've done? Because it goes from orange to green. So, you guys aren't going to find that funny. Yeah, this is going to go from orange to green, and therefore we're going to know it's an alcohol. But the problem is we're going to have that limit of, well, hang on a sec. It could be any secondary, it could be any alcohol. It could even be butan-1-ol. All we know is that it's not going to be methyl propan 2-ol. That's the only thing we know, because it's not going to be a tertiary. But there's limitations, because what it doesn't do is it won't distinguish between the isomers. That's the one thing it really won't do. We could then argue that you could actually distill the product and you'll realize that it's a ketone. Totally possible. But that's a whole different thing. That's not chemical testing, folks. That's a chemical reaction and then testing a product. That's not the same thing. Yeah, but we could argue that. We could then distill the products and then test it with Tollens reagent and it will give no reaction, therefore it's a ketone. But it's not really, it's a limitation on chemical testing. So we need to use other things, and IR is one of these. So what does IR give us? So IR detects the presence, I can't spell presence. Presence? No. How do I spell presence? I've honest to God, since I've been doing it online once, I just seem to have completely forgotten how to spell anything. Presence? I don't know. Presence? How do you spell presence? Presence. No, that present. Presence. Presence. No, I don't know. I've forgotten. Detects bonds. Lol. Oh, there you go. So I spelt it right first time. Thanks very much. It detects bonds. So how does it do this? So here's the description of what we're doing. So number one is we're going to have a sample of a compound. Now that sample is actually going to get placed into a really cool little jar called a cuvette. This is a glass cuvette. A glass, and I can't spell cuvette either, by the way. Cuvette. Is that how you spell cuvette? No idea. Cuvette? I only have ever written down the word cuvette. Let's see. Cuvette. Oh, go on. Do what I'm asking you to do, please. Or not, as the case may be. Images. No, that's definitely not that. Cuvette. I don't know. Infrared spectroscopy. There you go. How do you spell that? There it is. Sample cells. Well, that's weird. Oh, there you go. Cuvettes. Hey, there we go. It's more biology. Cuvettes. There we go. Thanks, Emma. Thanks for that. So a glass cuvette, and here's what they actually look like, by the way. It's nice to see this. There you go. So the cuvettes, by the way, these are actually made of a very special material. I wonder if you guys would be able to guess what the material is. The glass, it's actually a very special type of glass. And there is a good chance that you'd be able to guess this. The glass is pure silicon dioxide. It's pure quartz. Now, the reason for that is because it's a giant covalent structure. We know this. Yeah, silicon dioxide is a giant covalent structure, very similar to diamond. These are the oxygens. And then you have another Si. Yeah, another oxygen there. I think I might have put those in the wrong place. Not that it makes any difference, actually, to be fair, because it really doesn't. I'll see if I can find a picture of that, because it's easier for me to, because drawing pyramidal structures like that or tetrahedral structures like that is a nightmare. Silicon SiO2 structure. There we go. So why would I want to use a material such as this? The reason being is because it's giant covalent, the bonds are very, very rigid. Bonds, very strong, very rigid. Now, what that means is they're not going to absorb the energy, because what's happening here is that when you shine when you shine UV light through this cuvette, so this is, sorry, UV light, infrared. When we shine the infrared light through the sample, let's fill the sample up with something. There we go. So when we shine the IR through it, some of the energy gets absorbed. So, and the reason why it gets absorbed is because bonds, so let's look at water as a great example. So these bonds are polar. What that means is they're actually going to be able to absorb infrared radiation. And what this means is that they're going to then vibrate more. This, as a consequence of that, the molecule is going, those bonds are going to absorb it, and the molecule's going to start vibrating more. Now, it actually gives you a quite neat thing here, because the molecules don't just vibrate, they actually follow a particular kind of vibration. So this is where usually I would do a dance in lesson. I'll see if I can draw this out for you. So water does two types of dancing. One is the bonds will move up and down. Yeah. So this is a bit like a flapping bird. Yeah. They'll just literally move up and down like this. They'll move up and down. So it's flapping up and down. The next thing is that they can do is the bonds can also stretch. They can stretch and contract. So there's bond vibrating, there's bond stretching. There's also the bond vibrating one can also be both in and outside of the plane. So what you can also, by the way, these are actually going up and down here like this. Yeah, that's what they're doing. They're moving up and down. I hope you kind of understand what I'm trying to say there. They're kind of pushing and pulling. Do you also know that the water ones are actually going in unison? Well, they can actually also not go in unison as well. That can also happen. So we can get one that's contracting and one that's stretching. Yeah, that can also happen. And that then will alternate. Yeah, that'll then stretch and that one will stretch and that one will contract. So it'll kind of, you can kind of, I can imagine that you guys can imagine me doing this dance. I'm really tempting to activate my camera and do a bit of dancing. Shall I do some dancing? I feel like I want to do some dancing. Yeah, let's do it. I have no idea how to make this work again. So if I go back onto StreamYard and go start cam, and then I could do this one here so you can see me at the side. Yeah, that works. So what we've got here is I'm desperate. Yeah, Winkit really wants me to do some dancing, I think, here. I think he does. So so we've got water doing, I've no idea, hang on a sec. I've got to see, I don't want to do that because then it looks really weird. Let's just do this one. So let's hang on, that one there. Yeah. So we've got water molecules. Oh, I've got to do it now, folks. We've got water molecules doing this. Yeah, they're doing the weights. But then we've also got them doing this, like a bird. But then we've also got them doing some major exercise here. And then we've also got them doing this, which is the vibration around, which is not in the plane. So rather than up and down like this, they actually can also go and also three-dimensionally. So we've got a whole load of different types of vibrations there. Let's see if I can then go back to sharing my screen. No, bring it back. There we go. And then I'm going to turn my camera. That was incredibly embarrassing, but awesome. Let's see if I can turn that off again. Disable. There we go. Disable my camera. So we've got all these different types of vibrations. And what IR does is different frequencies. Sorry, I'm trying to plug my laptop back in and I'm really struggling. The infrared causes these vibrations to actually happen. Sorry guys, my laptop is now being a nightmare. Okay, so different frequencies are absorbed by different bonds, which is really cool. So what that means is, and that's the key next note, isn't it? We've done detects bonds. We now need to do that. There we go. It detects bonds, but not only that, we need to make this note, which is different bonds absorb different frequencies of IR, of infrared. So all we have to do is shine, and by the way, we have a detector over here. There's our detector. And that detector, it actually provides the reason why I'm drawing this is because this actually explains what's going on with the graph. So let's now talk about what graph this produces. So the infrared graphs. Now, because of this rather unusual situation of we shine light through it, shine in IR, we see an absorbance. This absorbs some of it. Let's actually try and make this like a, there you go. The size of the arrow in this case is going to be the amount I shine in. And on the out comes less. Now consider what we're measuring here, folks. What we're measuring is how much has passed through it. That's really weird. Because now that we understand that it's what passes through it, yeah, what that means is on the y-axis, try and zoom in, it is actually percentage transmittance, not absorbance. They love this question at A-level because everyone says percentage absorbance because IR's about bonds absorbing the infrared radiation, and it's not. It's actually the stuff that isn't absorbed that we detect. Down here on the y-axis, sorry, x-axis, is wave number. I know physicists in the room, really sorry, per centimeter. This is the same as frequency. I'm really sorry, folks. I don't know why. I think the reason why they do this is to make the numbers easier. Because if you were giving frequencies, you'd have to give real frequencies to do with, the length of them, and they'd be really tiny. And it's easier to quote wave numbers. The numbers make a bit more sense. And it actually goes in the opposite direction than what you'd expect. I'm really sorry, folks. It's just the way it is. Yeah. So we've got the reason because we're going from high frequency down here to low frequency down here, which means you've got fewer waves per centimeter. I know, I'm sorry. But they love this question, folks. They love the idea of labeling the axes. Give the upper and lower boundary of the wave numbers. Convention. Why is the scale so weird? Yeah. So Winkit, the range is decided. Range decided by bond absorption. Bond absorption. Oh, gotta be careful there. Absorption. Yes, it is absorption. Or is it absorb? No, it's absorption. It's absorption. So is by the bond absorption, because you don't see any bonds. So there are no bonds that will absorb infrared radiation above 4,000 wave numbers. So there won't be any up here. So they just decided and made the numbers easier. You don't get any absorption below the 400 wave number mark. So the range was just decided, and then I think in reality you could probably make it an obscure number, but they just did 404,000 to make it easy, which is really nice. That all makes sense. Holy moly, I feel like I went really quick there. Okay, so they do love this graph. Now what this means is if you put the cuvette in empty, what graph do I see? That is 100% transmittance. Nothing has been absorbed. What a bizarre thing this is. Yeah, because it's you'd expect it to just be down here, but it isn't. It's actually at the top, and they have asked this. They have given you a multiple choice saying, if the cuvette's empty, which graph is the one that you would see? And the answer is you'd see 100% transmittance. And the explanation is because there is no sample, therefore no infrared frequencies are being absorbed. Yeah. Why does the cuvette not absorb any? Because the cuvette's made of silicon dioxide. The bonds are very strong and very rigid, therefore will not absorb IR. By the way, can anyone suggest a better material that would be even better at not absorbing infrared radiation? Wonder if people can do that. Lob it on the chat if you can guess. Okay, so now that we've seen what 100% transmittance looks like, no sample. Let's just put over the top, no sample. What that now means is when we get a sample, we get something really, really clever. Diamond. Well done, Dat. Spot on. An even better material would be diamond, but it's really expensive to make a cuvette out of diamond, so we don't. Surprise, surprise. So, okay. What that now means is, what happens when we now put a sample in? So, IR sample graph. Now, this is actually a very odd thing because what it means is, I'm going to try and zoom in. They are IR sample graph is you now. So we've got 400. By the way, I always label all this because I know for a fact that they do this a lot. And so whenever I draw out a rough graph, I really like to actually put down everything because I know they're going to do all this. There's 100 up there. Percentage trans. I'm just going to put that. So we now get a really, really odd graph because what we don't get are peaks. No peaks. No peaks. Troughs. We now get what are called troughs in infrared because what's happening is that you've got 100 and then you suddenly get an absorbance. And so what that means is because it's been absorbed, the transmittance decreases. And there you go. There's our sample. So we've now got a very odd graph at this stage because there appears to be two very distinct regions. The first region is this one. And just to give you a little bit more detail, that ends at 1500. That there, this region, I'm going to try and make that a bit thicker. There we go. This region here. 400 to 1500 wave numbers. That there is called the fingerprint region. Fingerprint region, otherwise known as the FPR. My hand was working faster than my brain. I've done it again. What's wrong with me? FPR, fingerprint region. So, by the way, you're not allowed to call it the FPR in the exam. I just like to call it that. It makes it easier. But this is called the fingerprint region. And this region is a mess. And it has a very distinct use because the fingerprint region, this region is individual for every compound. Hence the term fingerprint. Yeah, so we know that everybody out there has a distinct fingerprint. The police keep a database of those fingerprints to be able to compare crime scenes and all that jazz. Well, we've done the same thing for IR. So we can now, because of this fact, let's put that in a chemistry bubble. We love the FPR. We love the FPR because it makes everything a whole lot easier. Because due to FPR, we can compare the FPR, the FPR to a database of known compounds, get a match to identify unknowns. Now, this seems amazing. Like, it pretty much, at this point, I've actually had questions at this point in the lesson to go, well, hang on a minute, what's the point with us doing any more analysis when we can just use the fingerprint region? Great question. Okay, so what's the limitation? There is a limitation to the FPR. Can anyone like to guess? In fact, take a minute, see if you can identify any. So there's only one limitation as well. I wonder if anyone wants to post on the chat. Come on, guys. Post. I know that you guys are probably then a little bit delayed due to various bits. But what's the limitation of the FPR going to be? Isomers? Question mark? No. This is not a limitation. Infrared can be used to distinguish isomers. It'll ask you to explain why. FPR different for all compounds. For all compounds, including isomers. So what's the limitation? Good idea, Emmett. Nope. Including isomers. So no, not the limitation. Nope. Gonna put a big fat X through that. That is not the problem. You need the note though, by the way. I've given you that for a reason. They've done that in a question. So the limitation, it can't detect, oh, it can detect isomers. Yeah. FPR different for all compounds, including isomers. It can tell the difference. It can't detect compounds not in the database. Ivan, good answer. Well done. So, if compound, thank you. There's one more. If compound not in database. Great answer. Spot on. That is correct. All comparative. No, it's yes. You're kind of saying what Ivan said. The idea if it's not on the database, then you can't compare it. Yes, but that's not the other limitation. The second one is impurities. If you have impurities present, then your infrared will be off. Now, you will at that point get what's called a percentage match, but it's still a massive limitation. If you've got a mixture, if there are two or more compounds. Yes, well done, Ria. Well done. Good job. Yeah, impurities / multiple compounds. Multiple compounds. Well done, Ria. Good job. There's a smiley face for Ria. There you go. I've got a smiley face for Ivan as well. There you go, Ivan. There you go. Yours is bigger than Ria's. There we go. Impurities. So at that point, you're going to have confusion in your infrared spec. So how would you get over this problem? Another question commonly asked. So question, how can this be overcome? Not difficult, folks. Purify compound. Now, by the way, usually this is 2 marks. Purify compound will be the first one. The second one, oh, Ria, were you sad that your smiley face was smaller than Ivan's? Oh, I'm sorry. Oh, I'm sorry. There you go. Look. There you go. There you go. I'll even give you a look. There you go. Nah, that looks really weird now. I don't like it. There you go. Are you happy now, Ria? So, purifying compounds, the first way to overcome it, that's going to be the first mark. Yeah. But then the second mark is you're going to have to tell them how you're going to do it. So, this could be fractional distillation. Always a good one. Fractional distillation. Possible. If it's liquids, possible. Yeah. Could also use chromatography. I'm actually going to say column chromatography now, folks. Column chromatography. If you, by the way, if you actually put chromatography, they'll give it to you. Yeah. But it's nice for me to explain that there are actually different versions of column chromatography. Different versions of chromatography, and column is one of them. And it's the best one for purification. Yeah. Is there any other ones? Distillation. Yeah, that's fractional distillation. Yeah. That's all. So those two are good methods for purification. Some people might say, what about filtration? But that's, that's like year 7. So don't do that. Okay. So now that we've talked about the FPR, what we now need to talk about is this section. Yeah. All the rest of this, 4,000 to 1,500. This region now is going to get used. So 4,000 to 1,500 wave numbers. Yeah. This is now used, area used to identify specific bond absorbances. Area used to identify specific bonds. Okay, so let's now have a look at some of these bonds. So the first thing, I've got data. Yeah, there we go. So guys, you need to be super happy about this because you're gonna get given this table of data. You don't have to remember it. How good's that? Yeah, so this table of data is available and it gives you the bond absorbances. It'll tell you the range of each of the absorbances. Now, I'm just going to make a quick note of these two. Notice that they're the same bond. That's an interesting one to spot. OH alcohols and OH acids. Now, there are certain bonds which I need you guys to specifically learn. And these are the 4 I need you to learn. I need you to learn OH alcohol. I need you to learn OH acid. I need you to learn C double bond O and C double bond C. These peaks are super, super important because they come up pretty much every question. So let's have a look at what they look like. If I'm going too quick, just pause it, go back, note down those bond frequencies. You can even just, if you just Google infrared bond absorbances, it'll spit that data out on Google and then you can copy it down there. But in reality, there's more to this really because you don't have to know these because the data's there, but you need to recognize them. That's the important bit. Can you put a little subtitle of recognizing, what time is it? Oh, recognizing bond absorbances. Absorbances. There we go. Recognizing bond absorbances. There we go. So we've got wave down here. We've got percentage transmittance. I'll put trans there. Percentage transmittance. Okay. So I'm actually drawing the full. Can't be bothered. Don't read it. I'm looking at specific bonds now here, folks. So I'm going from 4,000 to 1,500. This now is going to be OH alcohol. So this is a very specific absorbance. Here's what it looks like. It's a big absorbance. Oh, it needs to be super smooth. There we go. That peak here, by the way, that little peak there is a CH absorbance, but this one is OH alcohol. And the reason why you know this is because the curve at the end is smooth. You are always smooth on alcohol. Okay. So that's smooth. I know it's not smooth because I'm just struggling to draw it on my laptop. I really don't like the fact that this is like, it's proper smooth. Like that. There you go. It's better. There we go. That's better. So that's the OH. It's a broad absorbance. So it's absorbing a lot. Now, just to tell you what this actually looks like, it's a broad, big absorption. So this alcohol groups are actually quite an interesting type of vibration. So number one, I think you realize that the absorption, hang on a minute. I want to actually emphasize the bond here that's doing the work. And that's this one here. So that one there, that bond has got a huge range, a big range of absorbances. A big range. Yeah. What that means is it's doing some major vibrating. And the majority of the vibration is actually like this. It's actually a rotation. So it's actually like, I'm trying to imagine how I could draw this for you guys. So if it was coming out at me, hang on, got an idea. If it was coming out at me like this, yeah, you can see this bond is coming out at me. What I'm actually going to do it. Yeah, it's coming out at me. What it's doing is it's actually rotating around in a circle. Yeah, and I really need to I'll see if I can find an image of this. I'm tempted to do, I'd be usually dancing in lessons by this point. Let's do bond rotating infrared IR spectroscopy. I don't know. I'd usually just be dancing to this. It makes things easier for me. Look at that. Scissoring, symmetrical, stretching, rocking. That's a great one. But the OH one is quite an interesting one because it's doing it's doing this. No, hang on. Oh, no, hang on. Can't find it. Oh, give me a picture. Yeah, I don't know. It's really annoying. I think you can kind of figure this out. And it's coming out at you. It's doing this kind of rotation. I don't know if you guys can understand what I'm trying to say here. I can't really think of how this. It's kind of like doing circles in the air with your arm. That's what it is. You're drawing circles in the air with your arm. Yeah, it has a huge range of absorbances. I really wish I could show you guys, but anyway, not that it matters. But the thing is, when it's doing this, it's doing it in a very smooth kind of rotation. It's very smooth. The circle is very clear. Yeah, it's going up and up and up and up and up like this. And it's a very smooth rotation. So it produces a smooth peak, which is that bit there. So what other one do we tend to see? Another one is the OH in the carboxylic acid. So again, looking at 1500 to 4000, this is percentage trans, and here is the OH carboxylic acid peak. Looks identical to the alcohol until, there we go, it is even broader, the range is even broader than the alcohol, but it is now no longer smooth. It is now being what is classed as distorted. Yeah, this is a distortion. And the question is, why is its rotation being distorted? And this makes total sense, because here's what's happening. We've got an OH bond here, which is trying to rotate like this. Yeah, it's trying to do that circular motion with your arm. But now what's happening is I have a lone pair on the oxygen up here and here. Now what happens, because of this lone pair at the top, the rotation of the hydrogen now becomes distorted. It's now doing this because it's being repelled by the O lone pair at the top. So you get this distortion of its absorbance. So it's a very obvious peak, and you can't really miss it. The next one that you need to recognize, is C double bond O. Now this bond has a very particular type of vibration, and this one is a stretching. This one likes to stretch. Now, can I just point out, it doesn't stretch by much. It's actually got a very limited ability to stretch. Yeah, it's kind of stretching within this kind of region here. That's like max stretch. Yeah, I need to try and make this more obvious. So it's changing from this length to this length and then back again. Yeah, so it's stretching a little bit, not by much, but by a little bit. Now, what this means is it doesn't absorb. Oh, why is the fingerprint region always in the 1500 to 400 region? That's a really good question. It's because of that. Okay, Kayan, great question. The reason being is when you get down to these frequencies, yeah, these low frequencies, what happens is all the bonds start to vibrate. You get a huge amount of absorbance, because essentially most bonds can absorb in this region. So they all start interacting with themselves, and therefore you get this horrible mess of peaks as they all bounce off each other, because most bonds will absorb in that frequency to some extent. So okay, now because the C double bond, see there's percentage trans again, I'm realizing I'm going to run out of time, and then wave number again. And in this case, for the C double bond O, I'm just going to rub that off and move it somewhere else. There we go. For the C double bond O, you get a very narrow absorbance. It's very sharp and very narrow. It looks like that. It's a very narrow peak, and it's at 1750. So it's a very sharp absorbance. Yeah. Very narrow due to the limitation on the kinds of vibration it can do, and because that bond is strong, which means it's going to limit its ability to increase in vibration. It's held very tightly. So it's a very narrow, sharp peak at 1750. There are small variations between aldehydes and ketones, by the way, but it will be on your data sheet when you see it. Okay, next one. So we are, and what's the C double bond C? Last one. Another. Now, C double bond C, again, very short, very limited vibration. Once again, it's a stretching. It's not a flexing, it's a stretching. And it's a very narrow, even, by the way, because it's now got atoms on either side as well, these also tend to limit its ability to stretch. It's even narrower than the carbon-oxygen double bond. What is it about polar bonds that makes them better at rotating and absorbing IR? Oh, that is a very good question, Ria. It's a very good question. I'm not entirely sure how to answer that. Okay, I can offer a suggestion, which is if you have a non-polar bond, yeah, if you have non-polar bond, the electron's density region is right in the middle, which means the attraction to the nucleus is either side is equal. So what that means is if I apply if I apply IR energy, what's going to happen is you're going to give the electrons energy and they're going to have an equal attraction to either X. What that means is even though they gain the energy, their ability to actually move towards somebody you're giving it the same energy on either side of the electron density, which means it kind of cancels out the ability for that bond to be able to absorb it. Does that make sense? That's the best I can give you, Ria. I have been asked that question in the past, and when I did the research, that's kind of what it describes. The idea that the electrons are evenly distributed, therefore the energy that they gain is even on either side, which means it kind of stops them wanting to absorb that light because it kind of cancels out the absorption. I know that seems odd, and I don't think it's a very good explanation in my eyes, but that's the best I got for you, I'm afraid. Great question. Just to give you this one, we now get a peak way down here, short and sharp, just to show you the difference. Yeah, that there at 1750, that would be a C double bond O peak. But this one is at 1650, and this is a C double bond C. It is shorter and, no, I wouldn't say sharper. It probably is sharper, actually. In reality, these peaks, by the way, they don't actually come to a point. They all actually have a curve on the end. Yeah, they are all curves. They're all absorbances, not spikes. Yeah, they are absorbances. So, but it's shorter and sharper. So that one's 1650. Now that actually brings me to the end of my lesson today. I've overshot already by a couple of minutes. And I've managed to cover all of my major things here. And I just thought I'd quickly show you a real IR here. So this is ethanol. So number one, let's box off the fingerprint region, the FPR. FPR. There we go. And then say, oh, look, smooth, big, broad peak at 3,300. There's going to be the OH-ol group. Yeah, I've also got a peak there that would suggest C double bond C, but it's not in this case. That's going to be the CC bond, I think. It'd be interesting to see if we can see the CC bond. Oh, no, yeah, there you go. CC bond. No, it's in the fingerprint. So it's not that. That's not that. Yeah, I don't... By the way, this is one of the limitations that we also come across in infrared. You always get these kind of abnormalities of people not quite where they should be. And I'll show you the questions that incorporate those next lesson. I'll do questions on IR next lesson. We have done bond absorbances and identifying particular bonds. Next lesson, I'm going to finish this off. I will pick up right where I was. And I'll finish off these two questions. Let's see if I can go back to my video. I'll reactivate my camera if it'll let me. Enable device. Go down to here, go to here, go to start cam. I'm nearly there, folks. Sorry about this. And then go to... That's my little fan. Let's go for front facing. There we go. Whoop, whoop. And go for that, guys. Right, year 12, thank you so much for coming. I hope it was useful. Do please spend a bit of time looking over the notes. I will, and have a look at the booklets. There are infrared booklets on there in terms of analysis. Do have a look at some questions. But I'm going to go through some of those. I'll post some more in the classroom for you guys to have a go as our homework. But I hope you found it useful. It's great to see you, year 12. I miss you all terribly. I wish we were at school. I miss seeing your faces. I miss having those chats. Make sure you stay well. Look after yourselves, guys. I really miss you, and I'll see you next lesson. Take care.